Great. Well, welcome. I want to thank everyone for coming out today, and folks joining us on the live stream as well. We'll be capturing this presentation so that others can view it afterwards as well. For those that I haven't met, my name's Eric Nordberg. I'm the Dean of the Library here at UT Martin. This is part of our UT Martin Research Series. We started this last fall. We're still kind of working on it, but it's a monthly series designed to highlight research here at the University of Tennessee at Martin. We're known generally as a primarily undergraduate university, and I think people don't necessarily think of us as being high research as far as our master's degree programs go, but meanwhile our faculty members are all involved in some very significant research. Today's speaker is a good example of that. We have a schedule set through May. Still trying to figure out if we're going to do some events over the summer. We might try a few, but we hope that you will enjoy today's February presentation, which was supposed to be on February 24th, but because of some inclement weather got pushed out to today. But our next event, the March event, the formal March event, will be on Monday, March the 14th at 3:30 in the afternoon. We're going to be having a conversation from Dr. Rasha Tawari in the Ag Department. She's also been selected as this spring semester's featured faculty member, which comes along with some accolades that you'll hear about at that time. And then if you're here April 6th, 12 noon, an event that probably would be good to be here in person for those of you watching on the stream, we will have Liz Alexander from the music department and other faculty members who form the LCD trio. And it's going to be interesting, I think, for them because their research is composing music. And so it'll be a good presentation that day. You can always look for information about our series on our website, also on our Runway feed, and then Facebook and some other social media. I want to thank Jennifer Petrovich, Catherine Brown, who do a lot of the work in promoting these events, beautiful graphics and good announcements across campus. Also Damon Ballou for his work from IT Services and helping us with the live stream. I really appreciate Dr. DeVito's willingness to share this as well and allow us to capture it. I do want to stress, though, that these events are intended to be in person, so please join us when you can. It's great to be able to talk to a presenter after they're done or before they're done, as we've seen today, and share information or gather more. So please plan to attend a future event. Just briefly, as an introduction, I could say that Dr. Jason DeVito received 2 simultaneous bachelor's degrees in both mathematics and physics, not surprising for today's talk. He also received a master's degree in mathematics. All 3 of those were from North Carolina State University. And then he went all Ivy League on us and got his PhD at the University of Pennsylvania in Philadelphia. That was in 2011, and then that same year came and joined us here at UT Martin, where he has quickly made his way through not only the assistant professor and associate professor levels, but achieved full professor status in 2021, which he pointed out to me means he has to serve on a lot more committees. So beware, those of you that are thinking about going for full professor. Today he's going to talk about his mathematical research. I did write this down. Manifolds of non-negative and positive sectional curvature, especially those with symmetry. He did tell me that none of us were going to be hurt in this presentation. Our brains are not going to explode or anything terrible like that. I do also want to point out that this kind of high-level research is rewarded by lots of different agencies. And in fact, Jason's working a grant from the National Science Foundation right now. He was a co-PI on a similar grant before coming to UT Martin. And so there are a lot of people who are very interested in this research and are supporting it with federal grant funds. He also received one of UT Martin's Reagan Leave Awards last year, which is a very significant award within our campus community. I always like to call out the fact, though, that he also co-chairs with Steve Elliott in the math department the annual middle school math competition in Tennessee. This is the one that's open to all Tennessee 6th, 7th, and 8th graders. And the reason that that's dear to my heart is that back in the late 70s when I was an 8th grader, I participated in a math competition and I actually won a trophy. And as a kid who didn't participate in sports, that trophy was like the bomb for me. So with that, I hope that you'll help me in welcoming Dr. Jason DeVito. Thank you.
Thank you. All right, well, thank you. As Dr. Norberg said, my name is Jason DeVito. Today I'll be talking about what the shape of the universe is, and I'm going to go ahead and preface this by saying there will not be an answer to this question. So it's very much so ongoing research, so if you're sitting on the edge of your seat going, but what shape is it? I don't know, but we'll talk about a few things on the way there. Okay, but thank you for having me. This is, I think, a unique opportunity to talk about math in a public setting. This doesn't happen very often, so I'm going to try to take advantage of it. So what I mean by that is, in terms of the outline, I'm actually going to spend more than half the talk not talking directly about my research, but just talking about what in the world is math research, and why should your tax money go to funding math research. And I'll admit, I'm not going to give the best ever answer to the second question, but I don't know, when you think about where all your tax money does go, a little bit going here, there, whatever, not that big of a deal. Okay, anyway, so you can see the outline on the side, but these are the three main topics. What is mathematical research? What's the point? And then we'll actually get into the main topic of the talk in maybe the last 20 minutes or so. So, yeah. And within that main topic, there's two subheadings. There's two different notions of shape that we will talk about. One is the geometry of space, and the other one is the topology of space. So this is going to be really the only technical terminology that comes up. I felt like I couldn't give a math talk with no technical terminology. That would be wrong. So geometry and topology. And most of you have heard geometry before, maybe not used as that kind of a part of speech like that, but we'll kind of address that when we get there. Anyway, yeah, let's go ahead and dive on in. So what in the world is mathematical research? And what I want you to be thinking about in your head right now is if I ask you what physics research looks like, or biology, or chemistry, or medical research, I think all of you have some kind of notion of what a physicist or a biologist or whatever is doing, you know, in their evenings in the lab or whatever. But when I talk about what is mathematical research, what do you picture me doing, like, you know, late at night in my office? But what kind of math? Like, what kind of math problems? Am I just like adding up really big numbers that won't fit on my calculator? Like, what in the world? Like, what is left to know? One of the issues here is, for most people's mainstream education, if you're not a math major or a theoretical physics major, the latest math you learn is calculus, which was invented in the mid-1600s. We don't teach any other subject like that anywhere. Imagine learning biology in college and all you learned was up through 1600, right? It's just, we just don't do that. But in math, that's how we do it. Whatever, for better or for worse. So what in the world is mathematical research? Well, it actually comes in two phases. And the two phases kind of set it apart from a lot of the other sciences in some sense. So the first phase actually has a lot in common with sort of more mainstream sciences. There's a discovery phase. What this is going to look like is you're going to be investigating some kind of known examples of mathematical objects. What do I mean by mathematical objects? Maybe numbers, maybe shapes. If you've had linear algebra, maybe we're talking about matrices. If you've had calculus, maybe we're talking about functions. If you've gone on to mathematical grad school, there's a whole zoo of objects that people care about. And maybe you're investigating some of these known examples, and you're looking for patterns. Hey, among these objects, all the ones with this property also seem to have this other property. And then you maybe play around with some other examples and say, oh yeah, this pattern is continuing. And then you make a guess. Maybe this pattern happens all the time. And that's when stage two of the mathematical research thing pops in, the verification stage. And this is very unique to mathematics beyond other sciences. So in other sciences, in physics or whatever, after you make a guess, you can go out and do 100 experiments and in a lot of ways confirm your guess. But this is known as inductive reasoning. It's when you look at patterns and you see a pattern, you go, oh, I bet this pattern continues. And it's a great form of reasoning. Like, the sun has risen every single day the last 37 years I've paid attention. It's probably going to rise tomorrow. There's nothing wrong with that logic, but it's not 100% foolproof logic. In math, we get the ability to use deductive reasoning, which is when we can proceed logically from things. Let me give an example. If you believe that all cats are cute, and you believe that I have a cat, then you are logically forced to believe that my cat is cute, right? Like, if you believe those first two things, this would be like carefully defined list of assumptions right there. If you believe those first two things, it is inescapable that the third thing happens. It's not a 99.999% likely chance. It's granted the first two things, the next thing 100% of the time must be true. And so again, math is kind of unique in that we are allowed to use deductive reasoning in ways that other sciences are not. And what that gets for us after we use a whole lot more. I mean, when I talk about using a lot, I mean sometimes 100-page long arguments, like very, very, very long strings of deductive reasoning. What we get is some kind of conclusion which we know with 100% certainty. And this, to me, is kind of mind-blowing. This is not something that pretty much any other science gets to have. In every other science, you can do 1,000 experiments, and if all 1,000 work, you can be like, really, really, really confident, but there's no promise that the 1,001st experiment is going to work. In math, because you can argue using deductive reasoning, you can know ahead of time they're all going to work, every single one. And it's a nice power. It's a nice thing. So I actually wanted to go through this process on 2 examples. We're not going to do the most earth-shattering bits of research, right here live, but we're going to do something. So here are our mathematical objects I want to talk about right now. We're going to talk about integers. So when I say integer, I just mean regular numbers. I guess I have a laser pointer I could use. Well, it's coming out of the thing. It's just not on the screen. Whatever. Okay, I'll just point. So we're talking about numbers 0, 1, 2. They're negatives. We're allowing negatives. Negatives are not that bad. No decimals, no fractions, but other than that, regular good old-fashioned numbers like everyone loves. And here's the official definition of what it means for an integer to be even. Even means you can write it as 2 times something, where the other something is itself an integer. So just to do 2 quick examples, 18, I think we would all agree is even. But according to this terminology, this definition here, the reason it's even is because I can write 18 as 2 times something, 9, and that something is a nice number. It's an integer. On the other hand, a number like 7, not even. Of course, you guys already knew that. But the mathematical reason is, yeah, I can write it as 2 times something, but the something is not a nice number. It's a decimal. Good so far? All right, so that's even, that's odd. And now what I actually want to do is have some audience participation. So here goes nothing. How do I get my toolbar back? I didn't think through this very well. We'll minimize. Sorry, give me 1 second. That's what I get for not thinking through things. Cursor down to the bottom. Thank you. This. All right, audience participation time. I want some even numbers. 4. I heard 4. I heard 8. Maybe 2 more. 10 and 24. Good, I can do math with these. The ones I practiced with were like 3 digits, just in case you guys are like firing off crazy things. So yeah, I can do these. What I'm going to do is add up, in various combinations, add these up, and we're going to look for a pattern and see if we can see it and then go from there. So I'm going to do 4 plus 8, and I'll do these kind of quick. I'm trusting you guys all have calculators on your phone. This is not showing up like I thought it would. So 4 plus 24 is 28. So that's what I've just done there. 4 plus 8, 4 plus 10, 4 plus 24. As long as I did the math right, we get these answers. So that's all the ways of adding 4 with the other numbers you gave me. Then I'll do 8 and 10, 8 and 24, 10 and 24. So 8 and 10 plus 10 is 18. 32. Okay, so you guys yelled out 4 numbers. I've added them up for you. I don't think I made a mistake, but who knows? Do you notice any pattern in the outputs? They're all even, and it certainly seems to be the case that these are all even. But now we need to take a step back. Is this an accident? Like we just picked 6 numbers. So step back. How many even numbers are there? Infinitely many. We just checked 4, and they're all even. Is that really a good reason to say, oh yeah, they're probably all going to work out to be even? Like if you check 4 out of infinitely many things, so let's make this like, forget infinity. If your boss is like, hey, we're shipping off, toys to kids who need them, I need you to check if they're broken. There's 50,000 toys and you check 6, 4, whatever. Like you didn't do your job, right? You have no basis for saying this is what the answer is. My students often will run with this and be like, oh yeah, it's always even. But I want to go through like the mathematical reason. Okay, how do we know that this thing is even all the time? So let's see. Back to the thing. All right, so how do we know it's even? So I'm going to state this in the form of a theorem. So the word theorem in mathematics means something that we know is true all the time because we have a deductive reasoning which establishes the fact that it's true 100% of the time. So the theorem just says, if I start off with 2 even integers and I add them together, the answer must be even. Not that just it happened to be for the 6 examples we just computed, but that this is an inescapable fact that it will always be even. And here's the proof. Here's how we know it's true. Here's the deductive reasoning which leads us to conclude this. So the main idea is, well, what do we know about M and N? What are our careful assumptions here? It's that they are both even, and that means I can write M as 2 times something. And let me try that again with less touching on the touch screen. We can write M as 2 times something, and we can write, I didn't even touch it. Okay. We can write N as 2 times something, right? So that's just, what does even mean? I can write it as 2 times something, where the A has to be an integer and the B has to be an integer. Now we just add M plus N. What do we get? M plus N, well, M was 2 times A, N was 2 times B. You just plug those in. And then you say, hey, look, both those things have a 2, so I can factor it out. And so, hey, look, you've written M plus N as 2 times something. That's what it means to be even. It's 2 times something. And that's how you know it's true every single time, no exceptions. So again, it's not something special about those 4 numbers that you guys called out. It has to work out every single time. And this is providing the rationale behind why it has to be true all the time. And again, because we have this logical underpinning, we can know with confidence that, barring human mistakes, which happen, this thing has to be true 100% of the time. Okay, make sense? Your first mathematical research ever. Good job. I want to do another example that's more geometric. I'm going to kind of skip the discovery phase because it takes too long to do. So in a lot of ways, that's the fun part. So I apologize for that. But I also want to show off another kind of hallmark of mathematics. And this example will show this better. Okay, so start with any rectangle. Could be a square, doesn't have to be a rectangle, but start with any rectangle. If there's a brick you're looking at, you can use that one, whatever. Pick a dot. I just picked 3 random dots on each one of these things. And now for any dot you pick, there's an opposite side, dot, opposite side, dot, opposite side. And we're going to make triangles using those opposite sides. And the question I want us to think about is, okay, we have an orange triangle inside of a big rectangle. How do the areas of the triangles compare to the areas of the rectangles? Obvious statement number 1, orange triangle has a smaller area than the rectangle it sits inside of. Duh, it sits inside of it. But okay, so is it like a third of the area? Is it half the area? Is it 9/10 of the area? Does it depend on the rectangle? Does it depend on the point you pick in the rectangle? Like, how much area is filled up by all of those orange triangles? And I'm going to spoil it. I'm sorry, like, this is a really fun exercise. I'm going to spoil it because I want to show this in a way that a lot of mathematicians really like. So I'm going to answer this question in a very, very, very simple manner, but the answer is going to come out of nowhere. And this is, if you've been in math class, this is how math works, right? There's a lot of this like brilliant insight things that pop out. This is not like something I created. This is someone else's thing, but it really shows what mathematicians value in their proofs. So what I'm going to do to answer this question for all rectangles, all points simultaneously, is I'm going to draw an extra line in the picture, right there. How does that line, so 2 questions, like where did that line come from? I don't know. Someone decided to draw the line someday. But the better question number 2 is, how does this solve the problem? Well, hey, look, now I have a small rectangle and a big rectangle, and I also have 2 triangles there. And how does look at the right side box. How's the area of the orange one compared to the area of the whole thing? It's obviously half. What about the left side box? Obviously half. That's it. So it has to be half all the time. And this is a really cool idea because it's one simple idea, draw the line. And it somehow cracks the entire problem, makes it obvious what the answer has to be without any serious calculation, nothing incredible. And these kinds of tricks or arguments are like gold to mathematicians. We're like, this is such a beautiful idea, like such a simple idea that can have such a grand effect on this problem, which could have been really difficult otherwise. So this is the kind of gold standard of what you're looking for in an argument. Is something that's really easy for anyone to understand, doesn't require like writing down equation after equation after equation, but they often end up having this feeling of like an idea pops out of nowhere. And it's easy to see how the idea solves the problem, but it's incredibly hard to see how anyone ever had this idea to begin with. Okay, so I hope I've given you a pretty good picture of what mathematical research is, but at least based on these 2 examples, there's a very obvious question of why would you pay money for this? Like, what does it do for anyone ever, right? So what's the point? So why does the NSF pay money for this? Why is this part of my job at UTM to do research? What's going on with this? And as I said before, I'm not going to give the best answer ever. I think you'll be a little bit unsatisfied by this. But let me maybe preface this by saying something like 98% of R&D, research and development, is a waste of money. But every now and then, someone has a brilliant idea, and you get Post-it notes, or you get Velcro, or you get something that changes the world somehow, right? So So maybe you should look at math kind of with the same standard as we view a lot of other research. But with that kind of in mind, here's where the funding idea goes back to. Does anyone know, well, anyone other than Dr. Guerin, know who this guy is? No one? That's so sad. His name is Alan Turing. Maybe that helps a little bit. So he does look different in the movie. You're right. He looks more like Dr. Strange. Yeah. So So he was a British mathematician active during World War II. And if you've seen The Imitation Game, you have a Hollywood version of his life story, which I'm not a mathematical biographer. Like, I don't really know extreme detail here, but yeah. So he was absolutely instrumental. The movie portrays him as cracking Enigma. Actually, the Polish mathematicians had cracked Enigma shortly after they were invaded and got the information to him about that. But after Hitler discovered that, hey, their Enigma cipher, this is how they were encrypting their radio broadcast to each other. After Hitler discovered, hey, that's been cracked, they introduced another one called the Lorentz cipher. And Alan Turing, yes, he had a team of mathematicians under him, but now that stuff has been declassified, like, a lot of the ideas were just his on how to crack this thing apart. So in some sense, not single-handedly, but the majority of the credit goes to him for cracking the Lorentz cipher. So that meant that during World War II, the UK and its allies got to know where the Germans were going to be ahead of time. And this was a huge deal, as you can guess. I was reading, one historian wrote that, in this historian's perspective, the fact that Alan Turing did his work shortened World War II by 2 years. So, I mean, again, not a historian, not jumping into that, but yeah, I mean, like, so basically ever since that, governments have said, well, maybe mathematics is worth funding, right? I mean, like, maybe this is worth throwing some money at and seeing what sticks, and that kind of thing. So that's historically, there was not a lot of funding for mathematical research prior to this, and then really after this is when it ramped up. So you can blame that guy for it. All right, so that's kind of the history on it, but I want to maybe get back into, like, okay, why? Like, what's going on here? When do people's results ever become important? And math has a habit of postponing when people's results become important. So it's very rare that someone does some work today and then tomorrow an engineer or a physicist uses it for something. What's a lot more common is that it's a much longer time frame and then it's used in a very unexpected way. So does anyone know who this guy is? I knew I should have put some Kardashian pictures in here just to get some yeses, but okay. All right, this is George Boole. That probably doesn't help. You guys probably have no idea who this guy is. Maybe some of you do. So in 1847, as quite a while ago, he wrote a paper called A Mathematical Analysis of Logic, where he talks about the mathematics of how logic should work. He talks about how the mathematics of truth values should work, true and false statements, that kind of stuff, how all that should work. And he actually gave a symposium on this where he said something like, I just did this for fun. This will never have any application whatsoever anywhere. But the math just worked out so nicely, I wanted to share it with people. And today we call his math Boolean algebra. And probably every one of you is using it in your pocket right now to play a phone game. So this math ended up being the mathematics behind how computer processors work. So that took 100 years before anyone implemented it. And now, great, things work great because he did work. So notice the time frame. That's what I really want to get at here. He was doing work before we had even harnessed electricity. Right? He was figuring out this kind of stuff. So, and just for fun, anyone know who this guy is? It's an actual photograph. It must be more modern. So this guy was, in the early 1900s, the premier British mathematician on planet Earth, which makes it really sad you guys don't know who he is. His name is Godfrey Harold Hardy. He went by G.H. Hardy. And in the 1940s, he actually wrote a book called A Mathematician's Apology. Apology in the sense of philosophy. So it was an argument for like what's going on in mathematics. And here's a quote that I absolutely love because of the contrast. So, I have never done anything, quote, useful. No discovery of mine has made or is likely to make, directly or indirectly, for good or ill, the least difference to the amenity of the world. Judged by all practical standards, the value of my mathematical life is nil. So here's a guy who did math for the sake of math and almost took pride in that. Like, this will never have any application to anything in the universe ever. His math is now used in RSA encryption, which if you've ever been on a website that says HTTPS, there it is. If you ever bought anything online, you should thank him. So, it's just kind of funny how it turns around. Like, so this is someone who purposefully kind of set out to be as far away from useful mathematics as possible. And the work he was doing is like 1910, so we're talking, less than 100 years later, we're using it all the time. All right, so I'm going to give you one more example. I'm going to guess no one knows who this guy is either. So this is Bernard Riemann. If you've ever taken calculus and you talk about a Riemann sum, it's the same Riemann. So he was active in the mid-1800s. I don't speak German, but in 1868 he wrote a paper called this, which birthed the field of Riemannian geometry, which is the research area I work in. He actually kind of did this on accident. So the way the German system was set up at the time was after you got your PhD, you did something called habilitation, which is like an extra PhD in some sense. And historically, you would present your advisor 3 topics to talk about. One of them is the work you've done the last 10 years, and 2 other ones are just throwaway things. And your advisor would, pick the first one, and you give a public lecture on it. Well, his advisor was a guy named Gauss. Maybe I don't know if you've heard of him, but a guy named Gauss. And he was like, I know your work. Let's do option 2, which was this. So this guy had to basically invent this math over a period of a month or 2. Gave a public lecture on it and birthed the whole math field. So he was a brilliant genius guy. When was Riemannian geometry used by non-mathematicians for the first time? Well, I'm sure you've heard of this guy. 1915, this physicist named Einstein came along, and he was thinking about, I need to know how light would respond if space and time were curved. I want to know what straight lines look like on curved things. Turns out that's what Riemannian geometry is. What does geometry look like if things are curved or in high dimensions or things like that? So Riemann had set the mathematical foundations for Einstein 50 years earlier. When has general relativity ever mattered in your life? I don't know about you, but I get lost all the time. So I use this all the time to get unlost. GPS runs on general relativity. So, here we are. That was more like a 2000s thing. So 150 years after Riemann, Riemann's math becomes useful to people's life. So there you go. And even 100 years after Einstein even used it in like a general physics theory, it became useful. So there's a large gap here. So I say that just to say I don't really know how my research is going to be used, if ever. It might not ever be used, but you just never know. There are some clever physicists, computer scientists, engineers, chemists, clever everything out there, and you just never know how they're going to take your math and run with it and do some amazing, amazing things. Okay. That is it for the first half of the talk, where I just talk about mathematical research in general, and now it's going to get to the gross, nitty-gritty details about what is the shape of the universe. And I want to start by asking a philosophical question. 2 of them, actually. I have 2 on the board. What do we mean by shape? And I'm not going to answer that. That's too hard. But are these shapes the same? So right now there's just one shape on the board. So yeah, it's the same as itself. There's another one. Are those shapes the same? And just to make sure we're clear, I just took the exact same picture file and copied it twice in the same dimensions. Yeah, so this is not a trick question. They look the same, but the answer is actually no. Because one's to the left of the other one, right? That's a difference. They're not the same. And now we're getting pedantic, right? So what are the rules of this game? What rules define when things are the same? Because you could always make up some kind of rule, no, that one's different, or that one's the same. If I only care about measuring lengths and angles and doing high school geometry, these are the same. But if I'm tiling my bathroom floor, placing one in one spot versus the other is different, right? So whether or not you consider things the same depends on the context. And I'm going to keep going with this. Is that the same as the previous ones? It's context dependent, right? If I'm tiling my floor, even though it's the same triangle just turned sideways, that could matter. But if I'm just doing high school geometry, it doesn't matter. It kind of all depends on what you're doing in life. And now I'm going to put something up there which now we're all like, oh no, that one's so different. No matter what, that's different. Until you see a rectangle, and then you're like, yeah, well, that one was still a triangle, so it's kind of the same as the first 3, right? So, and now we're going to blur the game even more. What if I start doing crazy things, or oh crap, circles? How does this fit into this paradigm? And figure 8s, and I copied this picture here just so you mathematicians are crazy. So we are absolutely nuts when it comes to creating crazy shapes. And so here comes the terminology for the day. If I talk about shapes being the same topologically, I'm referring to continuous deformation. So if you imagine building this triangle here out of, say, rubber, you just take a rubber string, make a triangle. I can take that rubber, and if I'm allowed to compress it or stretch it or bend it or whatever, I can make any of the pictures up to the circle. Right? I could just take that triangle and kind of stretch out the edges. I made a circle. I can't actually make the figure 8. Now, if you're picturing the figure 8 in 3 dimensions, as most humans picture the universe, the 2 parts are laid on top of each other, that's okay. But I mean in terms of the crossing points being the actual same point, that's a different shape than the other ones. Because on all the other shapes, if I just take one point and remove it, what's left is still connected. I still have one piece. But in the figure 8 piece, if I remove that center right at the x, I broke it into 2 pieces. That's some kind of fundamental difference between these kinds of shapes. And then vice versa, this one is just nuts. It's in its own category. Like if you delete that center point, you have 4 pieces. And you can actually extend this out fractally, so it's just the biggest mess ever. So from the perspective of topology, this is where we are allowing continuous deformations of shapes. The entire top row represents the same shape, whatever that word means, and the circle also. The figure 8 and the crazy thing are in a league of their own. On the other hand, if I'm talking about geometrically, what I mean, like if I'm studying shapes from the perspective of geometry, now I care about lengths and angles, in which case the first 3 triangles I'm going to call the same shape. They're going to have the same angles, lengths, and that kind of stuff. And then everything else is just different from everything else. Everything else has weird angles or whatever. So when we talk about shapes being the same, there's always do you mean topologically or geometrically? And the problems I love to think about are, if I know something geometric about the shape, what can I conclude topological about the shape? So that's the kind of, that's my wheelhouse. That's what I like to think about. So, okay. That is shape. So, I really want to focus on the curvature of the universe when I talk about shape of the universe. So, when you think about curvature, I'm thinking about how something's bending, right? So a sphere is curved, a plane on the ground is not curved. And I want to really get, in terms of the geometry of space, in that context of shape, how is space curved? And a very obvious question is, how do you measure that? Because when you picture a sphere being curved, it's because you take a step back from it. And you're like, hey, look, it curves inside of this overall 3-dimensional space that we live in. I can see the curving with my own 2 eyes. I don't know about you, but I have not found a way to escape the universe and take a look at it, right? Like we don't have that tool at our disposal to look outside of it. And so what I want to answer is, from a mathematical perspective, I don't actually know how the physicists do it, but from a mathematical perspective, how can you know something is curved without taking a spaceship flying away and taking a look at it from far off? So, I have here a sphere and a plane. So I want us to imagine for a moment that we live on the surface of a sphere that's so big that it looks flat. I know, controversial. Okay, how can we know that what we're actually living on is curved? Like, what kind of measurement could we do to say, oh yeah, this thing actually has to be curved. It's not actually flat. And to my knowledge, no one's ever done this on Earth. I'm not sure that practically speaking it really will work that nicely, but I want to give a nice mathematical answer. So just for concreteness, I'm actually going to imagine this sphere here as radius 1. Just so I can actually do some calculations. I'm going to bring the math, like, I couldn't give a math talk with no calculation involving geometry on a geometry talk, so we're going to do some calculating here. What I'm going to do with this is I'm going to start at the north pole on the sphere and start at the center point of the plane, and I'm going to traverse a distance in what appears to be a straight line. So it's not actually straight line as you can see on the sphere, but if you're just walking along and you're stuck to the surface of the Earth, that's what feels like a straight line. You don't feel any acceleration as you walk along the Earth this way. And the distances, I'll do the math in a second, but if you were to take that red piece of string on a line of longitude of the Earth and straighten it out and put it up against a ruler, I want the length to be pi over 2, which is approximately 1.57 whatever units we're in. Okay? And I'll show you where that number comes from in a second. We're going to go the exact same distance out from there to there. So the distance of that red thing and the distance of that red thing, the length of that red piece are intended to be the same. Okay. So we're not just going to head out in this one direction. We're going to head out in every possible direction we can go and then kind of mark the endpoint we get. So in the plane over here, if I also walk out this way and this way and this way and this way, and I go the same distance every time and I mark the boundary point, what do I get at the end of the day? You get a circle. How about on the sphere? Well, I'll draw the picture and then see if you believe it. So here, like if I go down this line of longitude, I land there. That line of longitude, I land there. I need to stop touching this. But you can kind of see along the different lines of longitude, it'll just hit a point on the equator. And the reason I picked pi over 2 was just so it lands on an equator so I can draw things really nicely. Okay, so the question that I want us to think about then is, okay, I have 2 green circles. Imagine these green circles are built out of string. Like you can actually mark all these points as you're walking. Someone can walk along with a piece of string, then you hold the string up next to a ruler, right? You can measure the length of this thing. How does the length of this green band around the sphere compare to the length of the circle in the plane? And we're going to compute this, because I don't know that it's obvious from the picture. So here goes nothing. Probably fastest to go like this. There's probably a smart way of doing this. I don't do things smart, I just get them done. All right, oh, I don't know what happened there, too far. All right, so we have the sphere. That was a radius 1 sphere. And we have our plane. I'm going to draw that first line. I had it in red a second ago. Let's see. I don't know how to select colors. Maybe this will be red. I had this line a second ago on the sphere. I have an arrow. I don't know how I did that, but I'll run with it. Okay. So if I kind of complete this into a line of longitude, I actually get a circle there, right? What is the radius of that circle I just drew? If the original sphere had radius 1, what's the radius of that circle? 1, right? So that circle has radius 1, and high school geometry tells us that the circumference of a circle is given by the formula c equals 2 pi r. We now know that the radius is 1, so the circumference, the whole distance around that circle going this way, is 2 pi times 1, it's just 2 pi, which is approximately 6.28, whatever. So where did that magic pi over 2 number come from? Well, if you take this 2 pi and do a quarter of it, because that's a quarter of the picture right there, a quarter of the 2 pi ends up being pi over 2. So I'm not going to write down that math here. You can just believe me on that. If you take 2 pi and divide it by 4, the 2 over 4 makes a half. So pi over 2. So the output my eventual circle at the end was this guy right there. That equatorial band. What's the radius of that circle? 1. So its circumference is 2 pi. So if I go back to the original picture, for the green circle on the sphere, the answer is 2 pi is the whole length around. Okay, in the plane, let's do the same calculation. I go out a distance. We decided it was pi over 2. That looks awful. Let me try that again in black. And then we turn this into a circle. We use the same formula. C is 2 pi r, but my r in that case was pi over 2. So now I'm plugging, like over here I was plugging r equals 1. Here I'm plugging in pi over 2. Those are different. I'm plugging in different things, right? So that's it. The measurements are different. And in fact, if you actually compute out the answer you get, let me go back to the slideshow. If you actually, use decimals and all that kind of fun stuff, the total length of this green band around the equator is about 6.28, and the total length around here is 9 and some change. It's pi squared is what it actually ends up being. So the point is it's bigger. Like going around the sphere takes less rope. So in other words, what a sphere thinks of as a circle of radius pi over 2 has a smaller circumference than what a plane thinks in the same situation. And that's a measurement you can actually do. So if you, I don't know, go stick a post in the Arctic Circle, take a, tie a, I guess that's ocean, maybe that won't work. I don't know, whatever. I'm not a geologist, but this is an experiment we could actually do. The Earth is actually, it's not a perfect sphere, but it's close enough that this experiment, I think, could in principle be done, especially if you're willing to cut down everything in the path of the rope. Maybe it's not the most ethical thing in the world, but yeah, I mean, so maybe we can actually convince the flat earthers. I don't know. Anyway, so there is in principle this way by measuring what you expect a circumference to be versus what it actually ends up being, that you can tell these things are curved. So that's kind of the point of this. And in theory, you could do the same thing in the universe. Start at Earth, fire a spaceship off in every direction, measure the surface area of the sphere you get, and if it's not what you would get in normal flat stuff, you live in a curved universe. So I don't know that anyone's going to do this, but we could do it. What I do know is that physicists have done something. I don't know the details of it, but they have measured the curvature of the universe. Not a physicist. They did it. And most of the data says flat. Most of the data says, yeah, everything kind of looks like a plane. I mean, a three-dimensional version, right? We live in 3 dimensions, but a three-dimensional version of that. However, some data seems to be better explained if you say maybe the universe is actually spherical. Maybe it actually, shortest paths tend to come together, like lines of longitude eventually come together. Maybe that's what things actually do in the universe. And some of the data seems to indicate that. And so, as a mathematician now we have a well-defined mathematical problem. I want to know what are all the three-dimensional shapes whose curvature at every point in every direction is either flat or a sphere. Because as far as we can tell from our measurements, this is the universe we live in. It has this property. So I want a list of all shapes. And here in this context, I'm talking about topological shapes. So we're allowed to continuously deform things. I just want to kind of get a broad picture view of what we live in. And the question again is, okay, what are these shapes? So we have these special assumptions. Space has no boundary. Like you never just fall off space if you keep heading out some direction. That's this assumption. I think that's reasonable. There's another assumption that goes in, which is maybe not the most reasonable. So it's that zoomed in, if you zoom in on space, it should look flat. This is something that Einstein assumes in all of his general relativity. It's built into it, and so everything works great if your math is coming from general relativity. If you've heard of quantum mechanics, this is very not okay in quantum mechanics. So this is not the best assumption ever, but mathematically it actually gives us a problem we can solve, and good news, we've solved it. So notice the dates here, right? This is not Newton did this in 1600s. This happened for some people in their lifetime, right? I mean, wasn't that long ago for all of us. So 2 results, one by Cheeger and Gromald, one by Hamilton. So Cheeger and Gromald did the case where the volume, you assume the volume is infinite. What shapes do you get? That's their result. And Hamilton is, what if the volume is finite? What shapes do you get? We have a list of all of them. There's infinitely many, but we know that the list is complete. Like anything that has this kind of curvature, 3-dimension, meets these assumptions, must be on the list, one of the lists that these guys created. It's just groundbreaking work. These were all published in like very, very high-tier journals, huge results. The Cheeger-Gromald result is not unique to 3 dimensions. It's a general statement, like it's huge stuff. So you're probably wondering, well, what are the shapes? What do we live in? We have this list of things. Yeah, it's infinite, but at least we have it kind of narrowed down a little bit. It's not some arbitrary, terrible list. Well, as I said, it's infinite. So instead of trying to tell you what that is, I'm going to tell you what the answer is if we imagine we lived in 2 dimensions instead of 3 dimensions. Because here I can draw pictures. We can actually see them. And more importantly, instead of getting infinitely many, we get 7. So that's a number I'm willing to put up on the board. Before I put those on the board, we have to have a quick conversation. You guys recognize this, right? This is, if you're thinking Pac-Man, you're wrong because she has a bow. This is Mrs. Pac-Man. And what I need from this screen, I scoured Google Images for something useful here, and this is what ended up popping up. What I need from this, the reason Pac-Man is coming into a math talk, is what happens if Pac-Man or Mrs. Pac-Man goes that way? Back on the other side, right? She just appears right here. If you were programming this, would she have to come out here, or could she come out down there or down there? You can make up whatever rules for the world you wanted, right? Like she doesn't have to. There's nothing like inherent in video gaming logic that means that when she goes out that way, she's got to come out that way. You can make the rules whatever you want. Now you would want some kind of consistency. So if coming out here means she appears there, and coming out down here means she appears there, you have a problem, because what if she backtracks? Which one does she come out of, right? So you want some kind of consistency. These things should be paired up somehow. And you're like, okay, this one, this is the entrance and exit, this is the entrance and exit. But whatever, as long as you're consistent, it's okay. All right. Hold that thought. Here are the 7 pictures. The pictures that have dots on them, the kind of bottom 4 pictures, you have to interpret with Pac-Man eyes. So that's the trick. So we'll get to those in a second. Let me talk about the top 3 because they're a lot more straightforward. If you live on a 2-dimensional thing that's curved like a sphere, it might be a sphere. Deep thought. Now let's back up. I'm saying 2 dimensions. When you guys think of spheres, do you think of those as being 2-dimensional objects? No. So this is a language difficulty that I struggle with because I'm so trained in the mathematical terminology that I'm using English words in a way that you guys aren't using them. So let me take a step back. When a mathematician talks about dimension of a shape, he or she is referring to the number of coordinates I need to tell you to specify a point on the shape. So if we're going to meet somewhere on the surface of the Earth, I need to tell you a latitude and a longitude. 2 numbers. In that sense, the surface of the Earth is 2-dimensional. 2 numbers are sufficient to determine anything. So it's in that sense that we're talking about 2-dimensional things. Same thing with the cylinder. You can see here it's a hollow cylinder. So in order to meet up on a cylinder, we have to decide how far left and right to go along it and how far around. That's 2 numbers. 2-dimensional in that sense. Okay. So with that out of the way, what are the 2-dimensional shapes that are in every direction curved like a sphere or a plane? Well, there's a sphere and a plane. Those are not surprising. The cylinder, you have to do the calculation. You have to draw some circles and measure radii and that kind of thing. But it turns out that on the cylinder, you get exactly the same answer for radius of circles as you do in this picture, as long as the circles don't wrap all the way around. So as long as you're short enough, small enough circles, you get exactly the same measurement. So the cylinder is actually flat, which is kind of a weird idea. Said another way, if you were to start at a point, go out, however far you want along a straight line, another one, you make a triangle. In this picture, the angles add up to 180 degrees. Everyone knows that. And it turns out in this picture they do as well. But in this one they don't. So that's another way to say this. Like straightest paths kind of go weird in these things. Okay, so those are kind of the three straightforward ones. Now I'm going to talk about the four at the bottom. Again, the dots are supposed to indicate Pac-Man things happening on. So if you match up dots, that tells you where the entrance and exit points are. So for example, on this thing on the bottom left over here, there's a green dot on either edge. And what I mean is if you go down the sphere, the hemisphere down there, you pop up here coming up. Or if you go down the front, you come out the back coming up. So that's how the Pac-Man doors work on this one. This one here, if you go kind of through the middle of the plane, you just pop back on the other side. But as you go higher over here, you appear lower down there. They're kind of offset from each other that way. You could actually build this shape out of paper. It's called a Mobius band if you've ever messed with it. So, and if you care, my wedding band is one of those. So if you want to look at it after the talk, you're welcome to. So, go nerds. So that's that one. This one here, you can actually also build in real life. So this one is a cylinder, and if you're on like the cylinder right in front of you, and if you're on the front edge of it, and you go off there, you appear in the kind of the same spot. So just along the top, you stay along the top. The other one, top stays on top, bottom stays on bottom, but the front face of the can of soda is how I'm thinking about it, becomes the back face. It reflects back. This one cannot be built in 3 dimensions. Like there's no way to like create this shape out of paper. All the rest of them actually, well, neither one can this one, but the other ones can. This one right here, you can imagine this one as you take the ends of your tube and just kind of stick them together and make a donut. That's another way to think about this shape right there. So, yay, donuts. Okay, so these are the 7 shapes, and just kind of seeing the complexity in like, hey, we're doing Pac-Man style things on 4 out of 7 of these things. You can imagine how much more difficult this gets in higher dimensions. And in fact, in higher dimensions, there's the analog of a sphere in higher dimensions. And then it turns out, built out of this, you can make an infinitely many like hemisphere different things, all with their own Pac-Man rules. And that's where the infinitely many examples come from. Okay, almost done. If we know the answer in 3 dimensions, what am I doing? Like, what's left mathematically to do? Well, I have some bad news for you. Physics doesn't end at general relativity, and physicists are nuts, almost as crazy as mathematicians. See, a lot of them are investigating this thing called string theory, and kind of one of the fundamental hypotheses driving string theory is maybe we don't actually live in 3 dimensions. Maybe we just think we do, which is kind of like, okay, well, how could you think you live in this and not be the case? And the analogy they've come up with, which makes a lot of sense to me, is from really far away, a garden hose looks one-dimensional. Like all I have to do is tell you how far down the hose to go. Like if you're a big person, like a human, for example, and I want you to grab somewhere on the rope, all I say is how far down the rope to get, right? Or down the hose to get. If you're an ant living on the thing, you care about how far you have to go around the thing as well, right? So it's the idea of string theory is, yeah, we live in these 3 dimensions that we know and love, but there's these other like curled up small dimensions, kind of like the angular dimension on a cylinder. And maybe those things exist. And even worse, string theory has lots of varieties to it, and they all predict a different number of spatial dimensions. And who's to say that like tomorrow they're not going to come up with some other thing? I don't know, N theory or O theory. I don't know. Like who knows, right? And then who knows? So for me, I'm still interested in what happens in any other number of dimensions. Okay, we know the answer in dimension 2, dimension 3 about these kinds of shapes. What about higher dimensions? And great news for me. Starting in dimension 4 and up, no one knows. That's where the research is. So what I spend quite a bit of my time doing is creating new shapes. Like, hey, look, they're curved like a sphere or like a plane at every single point, every single direction. And I do a lot of this work with undergraduates. It turns out you can boil a lot of this down to, can I solve this system of equations? So it becomes something undergraduates can help with. And every time we get one, you write a paper and tell the world, hey, there's this new shape that needs to be added to the list. And I'll also throw this out here, that really no one has any idea of when the list is going to be done. So no one's thinking like, we're almost nearing completion. Like there's not that feeling in the field. No one has any idea how to show the list is complete at this point. The tricks that people used in dimension 2 and 3 do not work in higher dimensions in the same way. And so, I don't know, we don't even have a good conjectural way of saying, oh, at this point we're going to be done. This will be the complete list. So, still very much so an ongoing and I think fascinating area of research. And that's actually all I wanted to say about my own research. That's where I fit in, is that one sentence. That's it. Okay. All right, that is all I got for you. Thank you so much for your attention. And I hope you were more entertained than you expected to be. That's the bar I set. So. I never connected those dots. So the comment was I also aware that basically George Boole is responsible for all research in the sense that anytime you search with the words and or, that's his math coming in. So.
It is absolutely one of the first rules you learn in library school as well for doing literature searches. Yeah. Other questions? I had a question. That is, are all mathematics professors as entertaining as you are in the classroom?
I don't know. I think I bring a unique enthusiasm is maybe a nice way to say it. So I get very excited about what I do.
Great. Well, I would thank the people that are here today, those that joined us online. You can find Jason DeVito's email address on the UTM mathematics department. I'm sure he'd be more than happy to take time out of his busy day to talk to you about the shape of the universe. And again, stay tuned for more events in this series. Perhaps you can help me thank Dr. DeVito for his presentation. Thank you.